So let's start up with today's lecture. So last time, we were discussing about policy gradients, and then we discussed a bit about how sensitive things are to hyperparameters, and then we looked at some practical aspects of what makes PPO work, or just on policy algorithms work. And hopefully in the current assignment, you will be implementing PPO, all the way from reinforced to PPO, which should give you a very good idea of the nitty gritties which are involved in these implementations. So now, so there were two parts of the practical RL lecture. So we were only able to cover one part of it, which was sensitivity to hyperparameters. So now, I'll begin with the other part, which was, issues in defining the state space, dealing with large action spaces, the reward design problem. And then I think we'll have some time to, start going into some advanced deep learning architectures. So with that, I'll jump right to, state space, action space definition, and then the reward design problem. So you all can see my screen, right? One second, I don't have my cursor. Manipulate. Is the screen fully visible or are parts of it hidden? It's fully visible. Okay, perfect. Okay, so let's go back to one problem that we discussed in some part of the lectures earlier, where we have the state of the robot, maybe of this particular cheetah over here, defined as location, rotation of joints of the image. We take actions which could be torques on each joint, and the reward function might be the velocity, which is the speed of the cheetah over here, right? So now let's look at what are some possible choices of the state space. So one possible choice of the state space is to only include the joint positions of the cheetah, right? And then we could learn a policy which maps from this state space to actions. Now, I mean, this is something we briefly talked about earlier also. So what if it is necessary to include velocity or acceleration as part of the state space? What can we do in that scenario? So one possibility is that we can expand upon the state space and make it explicitly include the velocity and the acceleration term. But the problem is, or not the problem, but the issue is that now we need to explicitly compute velocity and acceleration, right? And this is something we need to provide the system with, right? And because now the state space is larger, the learning problem will also become harder, right? This is what we discussed in an earlier lecture, that expansion of state space leads to requiring greater and greater amounts of data to learn, right? Or the alternate possibility is that we don't end up expanding the state space, but we end up including the position at the previous three time steps, right? So these are pretty much the two options that we have if my state space definition might not be complete if I only included the joint position, for example. So in this case, the problem is that this is non-Markov now, because I'm dependent on the previous three states. Now turns out that policy gradients that we were doing, do not are not really affected, but some of the Q learning stuff that we were doing, could become affected because we pretty much studied them in the Markovian setups. Right? So you know, the other possibility is just to redefine. I mean, the state space to include all these three things and call it ST prime. I mean, so I guess the reason I'm going over all of these is just to say that, a lot of this is just a modeling choice in how you are modeling it. Right? For example, if you make st double prime, which has xt minus 1 and xt minus 2, now you can just concatenate it and, for example, feed it into your deep network and just call it, one state. And now we can, learn the policy, same as before. This is Markov when st double prime, but although it is Markov, which means that I can pretty much use all the algorithms that we have discussed until now, but this doesn't really mean that we are going to be more data efficient in any way, right? So I think the takeaway is that if there is more information which we think is required in the state space, there are two options. Right? One is to explicitly include it. For example, I can explicitly include the velocity and the acceleration, which was st prime, which was this one. The other possibility is st double prime, where I just expand the state space and hope that my function approximator, which takes this state as input, can automatically figure out relevant information such as the velocity or the acceleration. And the trade-off is that if I am going to explicitly provide st prime as a human, I would need to write code which can compute these things, but my machine learning system will need to do less work, right? St double prime is is more general in the sense that as a human designer, I don't need to put in that much effort, but it also means that my machine learning system will have to do more work. So I see some questions coming on the chat. So in a custom made environment, would there be a systematic way to check whether my observation is a state observation or partially observable observation? So I think the answer to this question is if you know the dynamics model or not. So if you know the dynamics model, then you can check, right? Depending on that, if your state provides all the variables necessary to simulate the future, then everything is observable. But if those things are not observed, then it is partially observable. So I hope that answers the question, Dongchi. The other question which we are getting it, is it possible to use the RNN where the architecture of the network will take care of the history? Yes, it is possible to use an RNN, right? So the question becomes is, where you are using the RNN. Uh, so I mean, till the time you are using the RNN in your, actor and your critic, for example, in both of them, it's going to be just fine. And there are many different choices. We could use a feed forward network where you concatenate things. You can use an RNN on, as we will see, we could also use transformers. All of them are equally good to use. So the difference between using an RNN or concatenation, I think I think it's just a modeling choice. In a way, if you concatenate, you are going to have many more parameters, but you are not going to forget information. Versus if you use an RNN, there's going to be some averaging of the tokens, right? So RNN has fewer parameters. So some of this we are going to see in maybe later part of this lecture. How does concatenation using an RNN, and even going to more fancier architectures like transformers, affect how we represent sequences. So if there are very specific questions about this, let's hold it up till the time we reach that part of the lecture, and maybe that will provide much more clarity. right? And then the other question is, is it also possible to use features in latent space from multiple time frames? For example, IT minus one, IT minus two. I think yes, we can definitely do that. So Perry, what you're talking about is, not concatenating at the input, raw input level, but first processing things through, say, a neural network to get some features and then concatenating them.
Yeah, yeah. I think it's just in between the the dynamics, which is really small dimension. You talk about x t x prime x double prime, or the raw xt minus one.
Hmm.
I just saw some people talk about, there might you may be able to compress the raw observation into some much smaller latent space, but it's still detangled from the physics, like velocity acceleration, something like that. So I thought it's just in between these two ends.
Yeah, I mean, so I wouldn't really say it is in between the two ends. For example, if I were to concatenate at even the input level, right? I don't see why it is fundamentally different from concatenating at the latent feature level, right? Unless you are pre-training that latent feature computation,
Yeah,
right?
that's a good point. Yeah,
Yes, I think if you're simultaneously training, it doesn't matter. If you're pre-training, then yes, that does end up being a bit different.
yeah. Thanks.
Cool. So yes, I think these questions about RNN, transformers, or whether to concatenate are great questions. I think this is exactly why, as part of the course, we have these two lectures on advanced deep learning, where we hope we can cover some architectures and choices which are really relevant to sensory motor learning. So if I, maybe I did not answer your question completely, maybe Dhruv and Ayush, let's wait for a bit, and if it is still unclear, please bring it up. Okay, so let's move ahead. So so this is the discussion about the state space and how we model it. The other discussion is about the action, right? I mean, how do we choose the action space? So as we have seen that there could be two possible choices: either the action space is continuous or the action space is discrete, right? Now if you consider some typical domains where RL has been successful, like Atari or Go, the number of actions are not that big. Atari has 18 actions, and Go, for example, has 361 actions. But what about if we consider other systems, for example, recommendation systems? So suppose you have a newspaper website and you want to recommend news articles, or you want to recommend movies. Now, the number of possible choices of the news articles or movies is huge. It is much larger than 361. It can go into hundreds of thousands or even millions. So how do we represent actions if my state space is so huge, right? So that is what we are going to look in the next few slides, right? So for example, let's consider a scenario where we have multiple stocks, say A, B, C, D, and so on. And there are three possible things I can do. I can either buy a stock, sell it, or just hold it. And similarly, I could have different articles like A, B, C, D, and I could either recommend it or not recommend the article. Now what we want to learn is the policy pi. So one naive possibility is that I have one dimension for each action. So it's A buy, A sell, A hold. So I have all possibilities I can do with A, then for B, then for C, and so on and so forth. Right? So this is one possible way I can go about this problem. But the issue is that my action space is going to be really big. Now, why is that problematic? Because exploration is going to be very hard, right? Because now I'll have to try all of these actions to figure out which is a good action. So my exploration will become a big problem, which will inevitably lead to suboptimal or poor performance. Right. So, what is an alternative over here? So, one thing we could do is that we can go and expand or redefine my state space. Right. So, for example, I'm going to include the stock name or the stock ID as part of my state space, right? In addition to other variables that I might have, right? For example, the state could consist of, what is Nasdaq, what is the value of Dow Jones, how is the weather, is it the Democratic Party or the Republican Party who is in power, and all of those things which we might think may affect the stock price. But I'm going to expand that and also include the stock name as part of my state. Now, once I do this, the action is I can just have a three-dimensional action space, which is buy, sell, or hold. Right? So in this particular manner, I can really compress my action space. So this is reminiscent of what we were discussing in contextual bandits, right? Where we were including, part of the state as the context, right? So it's the same idea over here. Right? So I could take something which has a very high dimensional discrete state space, and by redefining the state, I can make my action space be much smaller. So the action space ends up being low dimensional, but it also comes at a cost, right? The cost is that if I need to evaluate, for example, what stock I should, buy or sell or hold, I would need to iterate over all possible stocks, right? So that I can compute, what action to do for each stock one at a time, right? But maybe that's, not too bad. And the other question comes up is, what if there is a new stock that comes in, or there is a new news article which I need to recommend? What do I do in that case? So, before we jump, into that question, does anyone have any questions on what we discussed on expanding the state space, or how we can deal with a large action space? No, I don't see anyone saying anything in the chat. I don't hear any questions. I guess I do get something in the chat. So Dongchi is commenting a possible solution is hierarchical policy. So in some situations, there could be a natural hierarchy in the action space. So in those scenarios, yes, I think using a hierarchy can help us deal with a large action space more efficiently. Definitely possible. But for example, with stock A to B, so for example, if I have a list of stocks, there is no natural hierarchy in that setup. So in setup that we have it, let's go for it. So, and I think Dhruv has another question is, could we use a tensor output which simultaneously tells us action for every stock? So I think if you're saying that, if you're commenting on the fact that we, need to iterate over all stocks and we can parallelize the computation, I think that's definitely possible to parallelize it. I guess the point I was trying to make was that if you consider the setup on, the naive setup, we get all the predictions from just at once, and all these predictions are relative with each other, right? For example, I will have a multimodal distribution which is on all these stocks simultaneously, right? Versus when I include the stock as part of the state, I don't get relative probabilities between should I buy stock A or buy stock B. right? I now get independently for each stock, I get the probability distribution over the actions. So there is a difference in what we are modeling. So I guess maybe I should modify this statement need to iterate over all stocks to say that. Does it does it answer your question, Dhruv? Okay, perfect. So okay, so now let's imagine what happens if I get a new stock. What can we do in this scenario? Does anyone want to take a guess or recommend something that we could do in such a case? So so Simon suggests that we can project in the embedding space. So I think that's an excellent suggestion. That if I have a new stock, one thing I can do is to represent the stock as a feature vector, and then use some embedding technique. For example, if I'm dealing with language, right? For example, if I have newspaper articles which are a collection of words, we could use language embedding techniques such as word to vec, or even models like GPT-3 to embed um, the newspaper article in to a constant size feature vector. So one question which comes up is how do I convert my stock or the newspaper into an embedding? Now that's an excellent question. I think depending on whether you have image data or the language data, I think there are whole courses you can take. For example, the NLP course, the computer vision course, to really understand how to compute this embedding. But the idea is, but I think the takeaway from this part of our lecture is that yes, it is possible to handle a large state space. And yes, if even if my state space is dynamic, we can very easily account for it and incorporate it by learning and embedding. So another question which is, so if you're using feature vectors, I will not moving to continuous space. For my state space is continuous, not my action space, right? Because I have expanded my state space st prime to have st comma stock name. So I would replace the stock name by the feature vector. Cool. So and so this is something which is an ongoing research area. So if you want more, if you want to dive into it in more details, I recommend looking at these papers. So this is what I'm going to say about large state spaces. Sorry, I'm going to say about state spaces and large discrete action spaces. So now there is also another question about large continuous action spaces, and specifically when you have a sequence of actions that we need to do. So we are going to look at how we could reduce the dimensionality in that case, and some of that we will look in a lecture on hierarchical reinforcement learning. But if there are any questions, so what does large continuous mean? Large continuous means that you could have many degrees of freedom. For example, you can have 100 degrees of freedom or 1,000 degrees of freedom actuator. So I'm not talking about the range of each degree of freedom, but I'm talking about the number of degrees of freedom. So if there are any questions on the how to handle large discrete action spaces, now is a good time. No, so let's march ahead, and let's consider the third part of the system, which has got to do with rewards. So until now in the course we have looked at many different algorithms for optimizing the reward function, but we didn't really spend too much time figuring out where do rewards actually come from. So rewards are often designed. For instance, if you are playing Atari games, the game score is the reward. Right? If, for example, I want this cheetah to run, then the speed of the cheetah is the reward. Right? But let's look at what happens when we you know attempt to design rewards. So consider this example, and suppose the reward I give is the speed at which this agent moves on the right, and I want to use reinforcement learning to make this agent actually walk. So now let's see what happens if we optimize it. So one strategy we could learn is to move right, but in the way you're seeing on the screen. So in a way, we are able to optimize the reward function, which is moving right, but it's not exactly what we expected. Right? We probably expected this humanoid to walk on its legs instead of putting itself on the ground and crawling. Right? So this is an example of a behavior where I am optimizing the reward function, but maybe in a way that is not the way I wanted it. So let's consider another example. For example, I have over here two blocks, the blue block and the red block, and I want to stack this red block on top of the blue block. So one natural reward function is, first I'm going to lift this block and then keep it on the blue block. So there should be some reward for the bottom of the block to be raised above the table, and then I can go and place it on the blue block. So one question I have for everyone is, do you think this robot is going to succeed and lift this red block if we provide the reward function which is mentioned over here? Like, so the reward function, you can think of it as the z height of the bottom of the block, of the red block specifically. So maybe let me rephrase the question. The question is, if I give the reward which is equal to the z height of the bottom of the red block, will the robot lift the red block off the table? So, what do people think? Is it going to lift it, or is it going to do something else? So I see, different answers, coming over here. Some people believe it could be lifted. Some say that, it could lift it to a height, maybe throw it, right? So, so one thing, which you should just, which, if you think about this, what comes to your mind is that there are actually many, many different ways to optimize the reward function that we just wrote down, right? So, for example, if this is the reward function, and let's see what the agent does, right? It ends up flipping it because that is also optimizing the reward function, and I end up in a local minima, right? So the takeaway is that given a reward function, there are many possible ways to optimize a reward function. Just like it could have thrown it, it could have flipped it, it could have lifted it to a height, it could have done any of those things, right? And we have no way of saying what to do. It will just choose one of those strategies which is consistent with the reward function, right? So now, if it is now flipping this block over, what do we do now, right? If I really want this agent to lift the block, what would I do? Any suggestions? So, one possibility is that we are going to add some additional constraints, right? For example, I might say, well, the center of the mass of the block should also be high, or both the bottom and the top of the block, need to be above the table, right? So I need to now start putting in these additional constraints to get the behavior that we want, right? So, as some people are pointing on the chat, maybe you can also put orientation of the block as a constraint, right? So that is another possible constraint that we could be putting in. So, you know, the point being that the reward function has many possible solutions. The agent chooses one of them, and many times the solution is not the one that we want. And this is known as a reward hacking problem, because the agent hacked the solution. And to overcome this, we need to do some kind of reward engineering. And turns out that this reward engineering is not very straightforward, and a lot of time is spent doing it. Right? So let's see one more example of this issue. So over here, we have this boat, and we are playing a game where I want to move the boat. Now this boat learns this weird behavior where it goes around and then it comes down. So now, if you notice, this boat comes to this point where these green things are lifting up. Turns out these green things provide, a turbo score, or a max score, or some points that the agent can gain. This agent has timed itself that it goes around and comes to it, so it can collect these new points which are now spawned, right? So instead of actually moving around in the game, it has learned the strategy of coming to the part of the game where new points are being spawned. So again, this agent is maximizing the reward function. Maybe it's not reaching the global maxima, but it is definitely getting some rewards. And this is, one more example of reward hacking. So, what do we do, right, when we are faced with these problems? So let's study this with help of a simpler example. So over here, suppose the agent state is represented by xt, which is the location of this white dot, and we can formally define the state space, right? And suppose the action that the agent has is to move this white dot by a small amount, delta xt, where delta xt is less than some constant c. So, for example, if I make one action, my agent might come at this location. If I take the second action, it goes in another location, and so on. And the reward function is defined as following. If I reach within a small radius of the yellow block, then we're going to get a reward of +1. So we can define the reward function in the following way. Right? If I'm close to my goal, which is xg, and if I'm close enough, and with the amount of being close at epsilon, I'm going to get a reward of 1. Otherwise, the reward is going to be 0. This is also known as a sparse reward setup. So now, let's see what's going to happen in the sparse reward, right? So one thing is that the sparse reward is actually easy to define. It's easy to define because I can just say, if you complete the task, the reward is +1, otherwise it is 0. So for example, in the block stacking example, I could say, well, the reward is +1 if the red block is in top of the blue block, and otherwise I'm going to get no reward. Now it is easy to define, but it comes at a cost, right? The cost is that in order to achieve the reward, you need to do a sequence of actions which actually lead you to the reward, right? So, for example, over here, if I'm trying to learn my policy, you know, I try out one set of actions, I reach over here, I don't, go to the goal. I try out another sequence of actions, I might end up over here. I try another sequence, So, all of these trajectories are equivalent for the agent because in all of those trajectories, it gets a reward of zero, right? So the agent is unable to develop, any bias towards which direction it should move in because it is getting no signal of what direction is the right direction to move in. Because my reward will only be gained if by random chance or by executing a random sequence of actions, the agent reaches the reward over here. Right? So why do I say random? The reason I say the random is because if my policy pi is say a neural network with some parameters theta, then at initialization, these parameters theta are going to be random, which means that the actions that are being predicted are also random. And if I get no reward, then there's going to be no update to those actions. Right? So what I'm really hoping is that by performing a sequence of random actions, we actually go and get the reward. Right? So while these sparse rewards are easy to define, there is a big exploration problem. Right? So just think of how likely it is for the robot to do a sequence of random actions to pick up the blue block and then keep it on top of the red block. Right? It's very unlikely that you would execute the exact sequence of actions to perform that task. So the takeaway is that sparse rewards are easy to define. There are less chances of reward hacking because by definition we only give a reward when the task is completed, but that leads to the exploration problem. So any questions on the sparse reward part? No? I guess I see one question. So can we give an add-on of -1 reward for every step the agent takes, making the reward more dense? So in this particular setup, even if we give a reward of -1 at every step, unless I reach the goal at least once, it's not really going to matter, right? Because for everything, I'm going to get a reward of -1, right? So what I will end up doing is I'll end up choosing smaller trajectories, right? But then you can give a reward of -1 at every time step. In that case, all trajectories are going to have the same reward, which is -n, where n is the number of steps in each trajectory. So just giving -1 is not going to help me solve the exploration problem. But I think the point that is mentioned on the chat, that maybe we want to give the agent more hints about where the goal is, right? So and that we can do by giving the agent some reward more regularly, right? Which is some notion of a dense reward. So what could be some choices of a dense reward? right? I mean, does anyone want to shout out, or we just write on the chat window? So as Gregory said, one thing could be giving a reward which is proximity to the goal, distance to the goal, right? So so one question which comes up is, so there's a problem that I wanted to solve, which is I want the the white thing to move to a yellow thing, right? And if I just give a sparse reward, that's being problematic. And as one comment pointed out, I mean, will it really matter if we scale the reward, say from +1 to +n? In this case, it wouldn't really matter, because reward scaling, because if I don't ever reach the reward, you know it's not going to help me learn, right? And then we said, well, let me make the reward more dense, and there are a couple of different ideas which are coming out, right? Maybe we can give distance to the goal, maybe some reward, some constant value if you move towards right of the obstacle, and so on, right? So there are many different reward functions that we could be constructing. So natural question comes up is there some theory behind what kind of things can I add to my reward function so that the solution to my original problem is unchanged, right? So let's try to formalize this. So suppose I have this problem, P, which is defined as we have been discussing, and we are learning a policy which solves problem P. Now, can I define a problem P prime with a modified reward function where I'm going to add this term F to my reward, so that if I learn a new policy pi prime, my pi prime and pi, you know, have the same optimal solution, right? In other words, can I find an F that I can add to the reward function so that the optimal solution of problem P prime is also the optimal solution of problem P? So if we can do this, that means that it will give us some guidance into how to modify the reward function. Is this setup clear? Right? So now turns out that there exist some choices of F, and in the most general form, if we have no additional information about my decision process, which means that I know nothing, more than the fact that I just need to add this term F, right? I mean, I am not assuming any additional knowledge other than knowing that maybe I have an MDP, right? Then a choice of F which works out is if I have some distance, some function of xt plus 1, and then I subtract the same function from the state at the previous time step. Now this is called as the shaping term, and therefore this is called as reward shaping. Now why does this term work? We'll get into this. Just know that this phi can be any arbitrary function of x, right? So for example, you know as we were discussing, as some people pointed out, that phi could, for example, distance to the goal, right? Xg minus x squared. Or if it's a reward function, it's a negative distance to the goal, right? So phi can be any arbitrary function of x. So the reason this works out is, suppose I have these modified rewards, r1 prime plus r2 prime plus r3 prime. I've just written it out. I've just expanded each one of these terms. So r1 prime is r1 plus phi x2 minus phi x1. This is the expansion for r2, and this is the expansion for r3. Right? Now, if you notice, 5x2, 5x2 cancel out. Similarly, these terms cancel out, and so on and so forth. So what I end up is, r1 plus r2 plus r3 minus phi of x1, right? Because it only depends on the initial state. If my initial state is the same, then this is just a constant. So if we use a shaping of the following form, as you can see on the slide, then the policy that we find with the shaped reward is the same, or is also the optimal policy for the problem without shaping. Right? And this result was presented in this 1999 paper. Right? And this provides some theoretical guidance on how to shape the reward function. So what we're going to do, next is to consider some a practical example of this shaped reward function and see if it works. But before I jump into it, I want to take a small pause and see if there are any questions about how we are modifying p into p prime, or any other comments or questions which are there. So I see some discussion on the chat window about why can we define the reward based on the environment when the agent is, for example, supposed to discover the environment. So so the agent is supposed to discover the reward, but the environment needs is defined by someone, right? So in the real world, someone needs to define or in any scenario, someone needs to define the reward function, and that someone is not necessarily the agent, right? And therefore, that entity which is defining the reward function can have much more information about the problem as opposed to an agent, right? For example, if I'm playing the game of Go, someone defined the rules, and as an agent, my task is to come up with a strategy to maximize my rewards, right? So that's just, reward is a property of the problem, and the agent is trying to solve the problem. Okay, so I think Ayush has another question, is saying what happens if we have discounted rewards. So in that case, for example, what you could do is you can do gamma times phi xt plus 1 minus phi xt, and then things would end up canceling in that case. So we can modify it to suit discounting. Okay, so let's see this in practice. What happens. So now, suppose I take a leaf, and we apply some kind of shaping, and suppose the shaping I'm going to apply is of the following form, right? Where I say, well, my reward is xg minus xt square, unless, so I've pretty much added this term to the reward function over here, right? I've just added the a shaping term, right? I mean, that's all that we have done. Now, if we add this term, will it work now? So, how many people think that, with this shaping term, my agent is going to now go to the yellow block? Anyone? I guess I see some things on the chat. So the obstacle would likely stop it, right? So now, consider, for example, this trajectory. Now I come close to the yellow block, right? And this is actually much closer than, you know, if I need to go like this, right? I mean, if I'm coming at this point to avoid the wall, at this point the reward is much lower, right? So this ends up being a local minima for the reward function. So my agent can just go close to the wall and get stuck over here. So this distance metric xu minus xc squared doesn't really account for the walls. So maybe what we can do is we can modify my shaping term again and shape it with some good distance metric, right? So a good distance metric, might account for walls, right? And might say that the distance between this point and the yellow block is very large, for example. And the question still remains, will this work, right? So I think if my distance is accounts for the wall, then surely I mean I will be able to go from my starting state to my goal state. But now the thing is, now we needed to come up with this good distance metric, right? Somehow I need to know in advance as a problem designer, I need to call the good distance metric. Now this is not straightforward in many scenarios, right? In the wall scenarios, it is somewhat straightforward, right? For example, I can discretize this grid. I can do a depth first search, or I can do a breadth first search, and I can construct a graph, and then I can count the number of edges in the graph, which go from so the white dot to the yellow dot, and that would give me a distance metric, for instance, right? But this becomes an involved process, right? So the takeaway is that yes, I mean in general we can provide more information, but providing more information is non-trivial. And the additional challenge is that there could be unexpected solutions that we might also introduce. Right? For example, consider back the block stacking problem. Right? Over there, we were trying to shape the reward function by saying I'm going to provide some additional reward to lift the block from the table, and not only to keep the block on the other block. Right? But this reward of lifting it created a local maxima, right, which led to reward hacking. So there are two issues, right? One, coming up with good shaping is not straightforward. And if you shape it too much, you're also opening a Pandora's box of allowing for much more reward hacking to happen. Right? So, suppose we, don't want to go into the Pandora's box. What can we do in that setup, right? So, for for a moment, let's assume that magically we can solve the exploration problem, right? I mean, what is this magic? I mean, we'll see in later part of the course that we could have different kinds of exploration algorithms. But for the sake of argument, let's assume we have solved the exploration problem, right? And my agent could go to the yellow block, right? So is everything good now, right? I mean, if we can solve the exploration problem and towards is everything good, or are there any issues over here, right? So the one issue which comes up is that both these trajectories that you're seeing on the screen are equally good now, right? If I'm getting a reward of +1, the moment I reach the yellow block, then both of these trajectories are good. Okay. But but we know that this one trajectory over here, the one with fewer number of actions, is the one that we prefer, right? So what do we do over here, right? So one thing I could do, which was pointed out earlier, is we can now add a negative incentive say minus zero point 0.1, so that if I'm not efficient at reaching the goal, I will take more steps and hence end up accumulating more negative reward, right? So what this would end up doing is this would end up prioritizing this particular trajectory over this, right? So this trajectory is not a good one, and under this incentive structure, right? So you know now let's assume that we have this particular reward structure, but we also want to penalize the agent for not, so we want to encourage the agent to not hit the walls without going to us defining this very good distance metric. So what I could do is I can have a penalty for hitting the wall, and then I can reset the game, or I can reset this environment, right? So for example, I can say, well, I'm going to get a sparse reward, but I'm going to get a very low value, or a very low reward for hitting the wall, and minus zero point 0.1 otherwise, right? So this could be one way for this agent not to hit the walls and this red wall in the middle, right? So now let's see what happens, right? So let's count the reward for this particular trajectory, right? It's minus zero point 0.1, and so on and so forth. So I get a reward of zero point 0.6 eventually, right? Okay. Now let's consider another trajectory. Now this one, gets a reward of minus zero point 0.3 if I just go and terminate in a wall, right? Now, you know, this is somewhat problematic, right? This is problematic because if you look at this trajectory, at some point you're getting a reward of minus zero point 0.4 over here, right? So if you were exploring, right, and if you were coming to around this point, you were getting a reward of minus zero point 0.4, and only if you took the next action you get zero point 0.6, right? So now instead of really following this trajectory and coming to the goal, you might just hit the wall and terminate, right? So it's possible that you don't end up exploring, but you end up going and hitting the wall, and you know you learn this strategy, which would again end up being reward hacking. So what did we do in the past, maybe 5 minutes, right? What we said was, or maybe in the past 10, 15 minutes, right? What we said is, well, if I can design sparse rewards which are easy, it's harder to hack them, but there's an exploration issue, right? Well, there are ways to modify the reward function by doing reward shaping, but turns out finding how to shape the reward function is non-trivial. We can construct good shaped rewards, but it requires manual labor. And if we construct them, we can go into some reward hacking problems, right? Then we said, well, defining this new distance metric, which to shape the reward is kind of difficult or is challenging. So let me try an alternative, right? For example, an alternative is maybe I put some penalty for hitting the wall instead of designing the distance metric. But these also run into the same issue of reward hacking, as you can see from this example over here, right? So I can learn this local optima of hitting the wall and then terminating. Right, so I'll take a small pause and see if there are any questions at this point. So did I answer the questions in the chat, or are there still pending questions in the chat? So I guess, Dhruv, you have a question saying, if you're able to solve the optimum reward problem, doesn't that mean that the RL solution is pretty unnecessary itself? Turns out not really. I think finding the policy turns out is even much harder than finding a reward function. So I think even if you know so many times you don't need to define the perfect reward function, but you can have a good enough reward function, which is much easier to design than trying to define what the policy is. So we'll see some examples in the course where you will see how some reward functions, which maybe are not the best ones, but are good enough to complete tasks. Okay, so so a similar issue can happen, just like we put a penalty of minus zero point 0.3 to hit the walls. Many times people want their systems to be energy efficient, right? For example, you could penalize the magnitude of actions to enforce that the system uses as less energy as possible. But we can inevitably run into similar issues of agent finding these kind of hacks, as we saw over here, right? So for example, if I have a negative penalty for the energy, the agent might decide not to move at all, right? Because that way it gets very little negative penalty. So I think if you're designing the reward functions, you need to think like a hacker. If I do something, what is how could my RL policy fool me or fool the reward function to solve the problem, right? So one needs to go down and really carefully balance these different terms which end up coming, right? And this is what people refer to reward engineering. And there's a significant amount of effort put in engineering these terms. So the right setting of these terms will help you solve the problem, right? So while we are at this, one question I could ask is, I put this penalty, for example, minus zero point 0.3 for hitting the walls, right? So they should discourage the agent to not hit the walls. So a question is this negative penalty for collisions a way to achieve safety? Right? So I mean, I'll open it up to people to respond. So how many of you think that this is a good way to make the agent be safe, and how many of you think that this is not a good way to achieve safety? I guess I should have had a poll, but I don't have a poll right now, right? So I think people nailed it on the chat that this is not a good way to achieve safety, at least at training time. So I mean, when you talk about safety, it's good to talk about what do I mean by safety. Do I mean by safety at training time, or do I mean safety at testing time, right? So if we say safety during the training is happening, then a negative penalty for collisions is not a good thing, because I need to first hit the wall, or I need to do the bad or the unsafe action to actually get the negative penalty for it, right? So at training time, by putting negative penalties, we cannot resolve the safety problem. For test time, maybe, right? Maybe if you were to optimize this reward function and you were reaching the goal, you will end up learning a behavior which avoids the walls. So at test time, maybe we are not going to be unsafe, about the things which were included in the reward function itself. Right? But it's still a maybe. More on this later. Right? The other thing to consider is, you know so why was this choice of reward function leading to hacking? And this was because this term, like minus point one, that you're giving every time step, which made going to this part of the arena or the environment be less conducive than just going and hitting the ball in one time step, right? So maybe in order to incentivize my agent to solve the task more efficiently, maybe instead of giving a penalty of minus point one, I could do something else, and maybe I can use the idea of discounting, right? So this is what we have seen before. Now, if I use a discount factor, right now, if I go over here, my reward is gamma to the power 5. If I go to take this trajectory, my reward is gamma to the power 10. You know, and I have a negative penalty on hitting the wall. Right. So now if I am in this area, my reward is still 0, right? But if I hit the wall, my reward is minus zero point 0.3. So now with this reward function and discounting, it is much easier to find the correct solution. Right? So this is one more motivation for discount factors. Right? I mean, we have seen previously how discounting can help us convert infinite time horizon problems to finite time horizon problems. How discounting can help us resolve credit assignment, but also discounting leads to bias at the cost of variance. But if in some setups it can help make reward engineering be easy. So I think the takeaway from this part is that depending, so there are many terms which go on design the reward function, and sometimes it is necessary to be careful, or you need to be careful in how you are using the different options that you have. Right? The different options are, you can use a sparse reward, but then you need to solve an exploration problem. So there are algorithms for exploration that we have a lecture dedicated to in the future. You could come up with a very good distance metric. That is a possibility. In some domains, the distance metric is well known, or is easy to estimate. In some other domains, you might want to include more additional terms, but they come with the cost of reward hacking. Then the additional constraints that you might want to impose, for example, being efficient, being energy efficient, being safe. And some of those things, if I'm including energy efficiency, it could lead to more reward hacking, right? So there's a trade-off over there. And similarly, some constraints could be achieved when defining the reward function. For example, for example, the policy at test time could be safe, but maybe at training time it is not going to be safe. So let's see how does this research look like practically, right? So for example, suppose I have this agent which I wanted to walk, right? So now you see this agent is not walking right now. It's failing. I suppose consider cheetah agent that you were talking before. Now you know we I look at this at this trajectory where the agent is not able to cross a large number of gaps. Then I'm going to maybe modify the reward function, and now maybe this agent starts running like this, and this is also unstable, and I don't like this behavior. Then I would look at this and again go back and modify the reward function, right? So in some ways, there is this loop which is there. I mean, if you are doing research in RL or using reinforcement learning to deploy something, this is how it ends up looking like a lot of the times. You look at the environment that you have, it doesn't behave the way you want it to behave, you come and you modify the reward function, right? So in some ways, what we end up doing is human reward descent. Coming up with different reward functions till the time you get the agent to do what you want it to do. And this is a big problem, right? And eventually you can make the agent work, but this is not ideal, right? I mean, this all the time we have been hearing that reinforcement learning can get these amazing results, but there's a caveat. The caveat is we need to define the right reward functions, right? So this is something which is typically not said, but it's an unsaid truth that there is a lot of work which goes in designing reward functions, right? For example, also consider this meta world benchmark which came out recently, right? This benchmark has these 45 manipulation tasks, right? Things like stacking blocks, pulling some objects, opening a window, closing a window, so on and so forth, right? So I'm going to pick up on one task, and in this task the gripper needs to go pick up this object and then move it. So let's actually look at the reward function for this task, right? So first, you know there is a reward for reaching. So now let's look at this, right? So the reward for reaching is minus of the reach distance. So it's a dense reward going close to the object. Now, if I am within, 0.04, then I use this. But, else I have a slightly different reward function. But if, you know, I am close to the object, then I also incentivize my fingers to close around so I can lift it. Right? This is just to reach to the object. Then there is a reward to pick up the object, and you see all these funny numbers, like zero point zero 0.04, 0.005. Someone came up with it, right? This edge scale. And then there's a reward to place the object, right? Again, you will see more funny numbers, like C1, C2, C3, which are defined over here. So this is almost like a program which was written to make the agent do what we wanted the agent to do, right? So I think the point of this is maybe educational in the sense that there are a lot of benchmarks which are out there for reinforcement learning. And if you just download the benchmarks, you will not realize how much work went into designing the reward function. And if you have a problem that you want to solve, how to design reward functions is not straightforward, right? And so in some ways, instead of having algorithms which can solve general sparse reward functions, a lot of practical RL systems end up being fitting reward functions to algorithms, right? Now this doesn't means that that's the end of the road. I think there is a lot of research happening to overcome this problem. One way is inverse reinforcement learning. One way is coming up, providing demonstrations to, or like learning from demonstrations, or even building good exploration algorithms, right? So these are some things that we will also look at in this course, right? How do we actually, where do these reward functions come from if writing them down manually is not so straightforward, right? So the problem is, we want to tell the robot to do something. The robot goes and does something, and then we are like, what happened, right? And then we go modify the reward function, right? And we should really ask this question, why is it so hard to tell machines, what to do, right? And in some ways the answer is, not, it's somewhat straightforward, right? The answer is that there are multiple ways which are consistent with the task objective, and and that is why the robot or your agent will pick up on any one of those. And that exactly is the problem, right? And this is what you can think of as the task specification problem, right? Specifying what to do is problematic. And you can ask the question, right? I mean, is it that we don't have the right language to specify tasks? I mean, a part of it is yes, because as humans, we would like to specify tasks in language, but machines don't really understand language, right? What they understand is mathematical formulas, which we give them a reward functions. So we need to fundamentally bridge that gap in how we as humans want to communicate tasks and the language in which machines understand tasks, right? So this is some discussion which I think there is a lecture that we're going to look at this task specification problem in more detail, because I think it's another one of those things where if you just pop out of your machine learning mindset, right? I mean, machine learning mindset always assumes that the task is specified and we are building algorithms to solve the task. But how to specify the task is not straightforward at all. So, before, I jump into some, you know, like some few things which are just good to know, I will see, if there are any questions. So there are some questions which are, great questions, but I'm going to take those questions after I get through some content I want to get through. I think these are more discussion based questions, so please, hold on, hold on for a bit. So I just want to, go through some definitions which are going to be useful in, rest of the course. So, one thing to distinguish between are these two problems, which are infinite time horizon and finite time horizon. I think we have seen bits and parts of it, but just to make it a bit more formal. So sometimes the goal of my decision making system is to maximize lifetime engagement, right? For example, or is to maximize rewards over lifetime. For example, if I'm Spotify, if I want to recommend music, I want this person to come throughout his lifetime to Spotify or whatever service I have. So I really want to maximize the rewards over the lifetime, right? As opposed to consider problems like picking and placing. So I'm just repeating this task multiple times, and I only care about whether I was able to successfully put the egg in the basket. Same when I'm playing this game, right? There's no lifetime element over here, but these are repetitive tasks that we need to do, right? For these problems are what are also known as episodic problems, or finite time horizon problems. Now, what do I mean by an episode? Episode is some fixed number of steps in which we want to maximize the reward. Although it turns out, right, that in practice we end up modeling infinite horizon problems also as episodic. Why is that? Because we assume a discount factor gamma, right? And the gamma naturally sets a time window, right? Because suppose if my gamma is zero point 0.9, then if I take 100 steps, then the effect of the 100 step is going to be very small, right? Because only zero point 0.9 to the power 100, which ends up becoming a small number. So depending on what value of gamma I choose, it really sets some time horizon, right? So I think it's, as a mental model, it's good to know about these two things, but also note that in practice we really don't use different methods to solve infinite horizon and finite horizon problems. I think the other thing to notice until now is that a lot of the problems that we have looked at are single task. Like for example, in the bandits lecture, we looked at saying how to show a particular layout to the user, right? Or playing the game of Go, or playing Atari game, right? In this, all of these cases, I was just trying to solve one task. There's only one goal, right? In Go, it is to beat the opponent. Over here, it's to maximize the score. But many times the tasks have different goals which I could have, right? For example, I could be stacking blocks in this configuration. So suppose I have, these are my four blocks, and these small spheres show the desired location where I want to put these blocks, right? So now I can move these desired locations could be anywhere on the table, right? So now it is not a single task, but there is a family of tasks, right? Similarly, if you want the temperature to be set at some particular value, say 70 degrees, right? Or for example, I want my balloon to be stabilized at some location, right? So these tasks are goal conditioned, right? And this is what we know as goal conditioned policy. If my policy contains the current state, but also some representation of the goal. So if you think about Atari games or DQN that you train in the assignment, the only state space input was the image. We never explicitly represented what the goal is. The only representation was through the reward. And we could do this because it only had a single goal. But in general, this is not true, right? We can have many different goals, for example, in these environments. And for those situations, we can construct these goal conditioned policies. Now, this is something again that we will cover in much more detail in a following lecture. And then, I think it's good to be aware of some more assumptions that we have been making, right? So one thing that we have really assumed is discrete time. And for discrete time, we have Bellman equations, right? I mean, what do I mean by discrete time, right? I mean, think about everything that we wrote. We wrote ST, AT, RT, then ST plus 1, AT plus 1, RT plus 1, right? So we were assuming there is some discretization of the time steps, right? And this discretization is independent of whether my state space is continuous, my action space is continuous, right? So there are three things that you could discretize, time, state space, action space, right? So we looked at what would happen if my state and the action space are continuous or discrete. But in all the algorithms, everything that we did until now, we assumed a discrete time space, right? But so just like we have Bellman equations in discrete time, in continuous time, we have this Hamiltonian Jacobi Bellman equations. And if you're interested in knowing more about this, I recommend looking at this particular paper, reinforcement learning in continuous time and space by Kenji. Right? There are some other assumptions that we implicitly made. For example, we have assumed the dynamics of my system to be stationary, which means that no matter what time I come in, the system behaves in the same way. For example, the equations of motions, right? They don't really change over time. So Newton's laws are valid. This is an example of stationary dynamics, right? But for example, consider the stock market. The dynamics over here are not stationary. Right? The way the system is evolving is changing over time, right? So it is a non-stationary system. So it's something just to keep in back of your mind that we have been implicitly assuming. So even in model-free algorithms, although we did not need an explicit dynamics model, we were assuming the dynamics model is not changing over time. And another natural place where this non-stationarity comes in is in multi-agent systems. It's something that we will look into in more detail, right? So with that, I'm going to stop, and happy to take a few questions